Okay, so comedian Bill Murray thinks that we can grow plants under reduced pressure, but this experiment doesn't seem to be working very well. The manometer here has a mercury fluid in it, very heavy mercury fluid, so it just a small difference in height represents a fairly large pressure difference. And inside this vessel is a reduced atmosphere, and there's a dying plant in there. And you notice that because it's a reduced pressure, the atmosphere actually pushes down on the mercury more than the atmosphere in the vessel does, and so the interface here is higher than it is on the outside. If this was a pressure vessel, it would be the opposite. So first thing is we have to decide where is the pressure going to be equal, and that would be at the lower interface of the manometer fluid, so that'd be right here. And the pressures on both sides will have to be equal. That would be here and here. The pressures are due to the atmospheric pressure here, and that has to equal the pressure inside the vessel plus the hydraulic head, which is basically just the weight of the manometer fluid from here up to the interface. So the first part was identifying that place of equal pressure. The second part is asking us what is the pressure on the right-hand side in newtons per square meter. We already know what the pressure is on the in millimeters of mercury, because it was given as 785 millimeters of mercury. You know that the pressure can vary. The atmospheric pressure can vary. It's not always 760 millimeters of mercury. So to convert that to newtons per square meter, then we would then say 785 millimeters of mercury. Use a picket fence always when you're doing unit conversions. Then we use the conversion table. And the conversion table shows 1 atmosphere is equal to, well, I'll write it down here, 1.01 times 10 to the 5th newtons per square meter. And that's 1 atmosphere is equal to that. Also, when this atmosphere is equal to 760 millimeters of mercury. And so we can cancel then units. Let's see, we can cancel the millimeters of mercury here and here, and we're left with newtons per square meter. And so the answer here then becomes, the pressure on the right-hand side then becomes 1.04 times 10 to the 5th newtons per square meter. If we equate the left-hand side pressure to the right-hand side pressure, we find that the pressure inside the vessel plus the hydraulic head of the mercury will equal the pressure outside on the open end of the manometer. So the hydraulic head is rho GH, which is the density, which I'll write as 13,500 kilograms per cubic meter times G, the gravitational force, 9.81 meters per second squared. And then the height was 10 centimeters, which is 0.1 meters. As often is the case here, we have a mass and a second squared there, and what we want is a force per area. And so that automatically makes us think of the G sub C. A Newton is a kilogram meter per second squared. Now I'm going to cancel out units and see what we have. So the kilograms here cancels with the kilograms here. Seconds squared cancel, that's good. We've got newtons and meters, so let's see what happens here. We got a meter here, cancels with this meter, and 1 meter here cancels with one of these, leaving us square meters. So we have newtons per square meter. That's exactly what we had the units for the right-hand side also. So then, this turns out to be 0.13 times 10 to the 5th newtons per square meter. So I'm going to go ahead and write the equation this way, that the pressure is equal to the pressure on the outside, which was 1.04, and then subtract that from the pressure due to the hydraulic head of the mercury, which is 0.13, and this is all times 10 to the 5th. That's newtons per square meter. Let's get a picket fence going here. And then we have to convert the newtons per square meter into PSI, because that's what's asked for in the problem. So we have 14.7 PSI, and then this is actually absolute, is equal to 1.01 times 10 to the 5th newtons per square meter, or pascals. So of course our newtons per square meter cancel, and I've got PSI. This is equal to 13.2 PSIA. This is less than atmospheric pressure. To get the gauge pressure, we subtract from this the atmospheric pressure. And in the solution I said 14.7. Technically I really should use the actual absolute atmospheric pressure, which is a little bit larger than this, but you know, my mistake, my bad. But anyway, this comes out to negative 1.45 PSIG gauge.